This is Differential Equations, section 2.1, Modeling with Systems. So this section is pretty important because the world is full of things that are connected. So the book starts with an example of predator-prey, and then it ends with a really fun thing about infected people, modeling epidemic. So because the world is full of interconnected numbers, we need to be able to model things that are systems of equations, not just one equation. So the book starts with this predator-prey model, and they talk about rabbits and foxes, and the population of rabbits goes like this, and the foxes goes right up after them, and then the rabbit population crashes, and the fox population crashes, and then you can see it as this kind of motion like this if you graph rabbits here and foxes here, and you can kind of plot those different possibilities. And then if you make the rabbits grow logistically instead of exponentially, then they kind of level out sort of the foxes, and you get this kind of movement towards equilibrium. So let's do activity 2.1.1 now. So activity 2.1.1, we've got those differential equations, and we're asked, how would you modify the system to include the effect of hunting of the prey at a rate of alpha units of prey per unit of time? So I've got x prime. Let's sharpie that too, so good. Let's move on to x prime equals a x times 1 minus x over n minus b times xy, and y prime equals negative cy plus dxy. Okay, now before I move on, I want to start to understand what this is saying. So here, the x prime will be 0 if x equals 0. So there are no prey animals. That number will not change because it'll be extinct. And if x equals capital N, the carrying capacity, then this part would be 0. But you still have the predators eating them. Okay, so this is, without predators, our prey fits a logistic model. So they grow kind of exponentially, but there's a carrying capacity, and they kind of level out towards that carrying capacity. Here, x times y, that's kind of the interactions between the predator and prey. And so if they're both, there's a lot of them, then x times y will be very big. If there's not many of them, x times y will be very small. So this model is kind of their interaction. And so they grow into a logistic model, but they're being eaten in a term that kind of models their interactions. The predator has kind of a natural dying off, but also grows with respect to when there's enough food, so when there's enough interactions. So here, we want to modify the system so that we're hunting the prey at a rate of alpha units of prey per unit time. So for part A, we just want to say minus alpha, because that makes, so if the prey is, say, deer, then we're allowed to, we're giving out this many hunting licenses a year, so we're pretty sure it's going to be that many deer killed each deer season. So that sort of thing. All right, part B. How would you modify the system to include the effect of hunting of the predators at a rate proportional to the number of predators? Well, here, really, there's two ways to answer this. And it depends on whether you think about this as, I really want to know these constants so I can put them back to the real world, or to try to make it the simplest mathematical thing possible. So if you notice, you've already got, use my mouse over here, or maybe right here. So we've already got the predator, you've already got it dying off at kind of an exponential, at a proportional rate. And so if you add hunting, it's just like a different proportional rate of dying. So you could just say the same exact thing. X prime equals ax times 1 minus x over n minus dxy. And then I'm not sure if I'm adding to part A or if I'm just doing my own thing here. I think I'm just doing my own thing. All right, so then y prime equals negative c y plus dxy, where this c is really the addition of two things. It's natural dying off plus hunting. Now for part C, suppose the predators discover a second, unlimited source of food, but they still prefer to eat the primary prey when they can catch them. How would you modify the system to conclude this assumption? Okay, well, that's pretty weird, of unlimited food, but here we go. So the prey is still doing this. So there's still going to be some sort of eating of the prey based on their interactions. But now, the population of the predator, if they have unlimited food, then that's just going to be constant growth. So positive c times y. I think there's other ways to try to answer this question. It's kind of a little bit vague, but that's the way I would assume it would be, is that you've got prey animals being eaten by predators whenever they can get them, and the predators kind of growing exponentially. Okay, what about D? Suppose the predators discover a second source of food that is limited in supply. How'd you modify the system to include this assumption? So part D, I'd have x prime equals ax times 1 minus x over n minus bxy, and then y prime equals c y times 1 minus, what should be our carrying capacity? Maybe capital M, y over m. So notice that in both C and D, there's really no prey animals coming into effect because the predator is getting enough food whether they catch this particular prey or not. So their population would not be affected by the number of prey. The number of prey is affected by the number of predators. All right, so part E, suppose that the predators migrate to an area where there's more than 5 times as many prey in that area, that they move away if there's fewer than 5 times as many prey as predators. How would you modify the system to take this into account? All right, now we're getting tricky. Okay, so the prey still follows the same thing. So for part E, we've got x prime equals ax times, let me make it so you can see, 1 minus x over n minus bxy. Okay, y prime. Let's see. What are we assuming here? So if the predators move to the area, if there's more than 5 times as many prey in the area, and they move away. Okay, so we've got, it's not clear to me if like all of them are moving away or if some of them are moving away. Let's just assume some of them are moving away. So in that case, we're gonna have two possibilities. So we either have, if there's if there's enough prey in the area, then here. So then we've got, let's go with those traditional like cy plus dxy, and then if there's enough prey, then we're adding predators from other areas. They're moving in. So then I need a new constant, and I don't like using e. So and I've got x and y, and so then I'll use k plus k if x is greater than 5y, and then it's negative cy plus dxy minus k if x is less than 5y. Okay, and then we don't know if that constant is the same or different. I think under these assumptions, maybe I can assume it's the same. Again, they are not being very clear, so it's fine. F, suppose the prey move out of an area at a rate proportional to the number of predators in the area. How would you modify it to take this into account? Well, now I've got f x prime equals ax times 1 minus x over n minus bxy, and then minus what, L? If x, let's see, move out of an area at a rate proportional to the number of predators in the area. So there's no prey moving in. Never mind. It's only moving out. So x prime equals ax times 1 minus x over n minus bxy minus, let's just use k, y, and then y prime would just be, I'm assuming we're starting from scratch again, so y prime is just negative cy plus dxy here. Okay, that completes activity 211.